Welcome to ChemDoctor, and the purpose of this presentation is to introduce the concept of writing an orbital diagram for a particular atom. Now, there are two ways to represent the electronic structure of an atom. One way to do it is through electron configuration, and I have produced a number of presentations that describe how to do this that are both on my website and on my YouTube channel. The other way is to utilize an orbital diagram. Why would you want to use one method or the other? So in order for me to describe the difference between the two methods, we need to go back and for a moment review the quantum mechanical model of the atom. Now, I'm not going to get into the esoteric details of the quantum mechanical model, and basically I'm going to boil that model down to a very simple way of looking at it. We can characterize an electron in any atom utilizing four quantum numbers. The first quantum number is the N number, and this is a reference to energy level. All right, and in other videos I've described the issue with that. So if we have some kind of atom that has a nucleus, I'll just put a plus sign in here and we'll designate this as protons. The energy levels begin with N1, which is the energy level closest to the protons, and then extend away from the protons. So, for example, N1 would be the energy level that's closest to the protons. N2 is going to be the next one out. N3 will be the next one out from that. Your N1 level is going to be the one that is lowest energy, the lowest potential energy, because it's got electrons that are in closest to where the protons are. N2 will have the next level of potential energy up from that because it's further away from the protons, and so on. And on the periodic table, the N numbers are going to extend up through N equals 7. All right, now we can also further characterize an electron. Besides knowing essentially where its electron shell is relative to the protons, we also can know the shape of the orbital it's in. And we can boil this down into something fairly simple. There's really only two kinds of shapes in terms of atomic orbitals. They're either spheres, or they're lobes. And for the spheres, it's straightforward. Each major energy level has at least one s orbital in it. So for example, N1 has a 1s orbital, N2 has got a 2s orbital, N3 a 3s orbital, and so on up the line. All right, now, every energy level beyond energy level 1 is going to have suborbitals that are lobes. It starts with the p systems in energy level 2. When we get to energy level 3, there are the d systems. When we get to energy level 4, we break out into the f systems, and so on up the line. All right, so an electron can be defined by its energy, by the shape of the electron cloud it's in. Thirdly, we can define its orientation, or the m sub L number. Now, in terms of orientation, if you think about a sphere, well, there's not going to be any orientation for a sphere because the sphere is going to be generated around some kind of an axis, like if you think about a basketball or a tennis ball or something like that. But for the lobe systems, there are definitely going to be orientations. So, for example, you could imagine, and try to think about this three-dimensionally, you could imagine a lobe that is like this on the x-axis, right? So it has an orientation relative to this directionality. By the same token, we could also have established it along the y-axis like this. So there's different orientations for the lobes. All right, first three quantum numbers. We can define an electron based on its energy, the shape of the type of orbital it's in, and the orientation of the orbital as it exists around some kind of an axis. And then the fourth quantum number is what I call the magnetic spin number. And this is a very important quantum number because what it does is it acknowledges the fact that electrons spin. And what the viewer needs to realize about this is that if you take a charged particle and you put a spin on it, whether it's a positive charged particle or a negative charged particle, if you put a spin on that charged particle, then it generates a magnetic moment, which is another way of saying that if you've got a charged particle that's spinning, then it operates as a miniature magnet. So electrons have negative charges on them and they spin. We can't know when we look at an electron whether it's spinning clockwise or counterclockwise. But what we do know is that in fact it is spinning. And so an electron will have a magnetic moment. Now, where this becomes important is when we have to pair electrons up into suborbitals. Because if you think about this from a physical point of view, when we pair two electrons together, they both have exactly the same charge on them. In other words, they both carry a negative charge that's exactly the same in magnitude. And in any classic physics class, one of the first things you learn is that when you've got two like charges, they repulse one another. Now, when we in chemistry tell you that we're going to be pairing electrons up, that should send up a red flag, because we're talking about putting two particles that have exactly the same charge into the same orbital together, and that's really, based on physics, an impossibility. But now, when you bring in this issue that the particles are spinning, what that does is it generates a miniature magnet out of each electron. So now, if we take an electron, the two electrons that we're going to pair up in an orbital, and we put them in there with opposite spins, then you can imagine a situation where this looks exactly like it does when you're playing with two magnets on the kitchen table. As long as you have the heads flipped around so they're opposite, the two magnets are going to be attracted to one another. They have a magnetic field which is complementary, and the two magnets have a magnetic force of attraction that draws them together. All right. So electrons, when they're paired up, must be paired up in those orbitals with opposite spins. And what this does is it sets up a situation where the magnetic force of attraction offsets the net force of repulsion, so that the two electrons can actually coexist in the same orbital together. And there's a famous scientist called Pauli who came up with what's called the Pauli exclusion principle, and what that principle says is that no two electrons can have the same four quantum numbers. And it's this last quantum number here, the ms, the spin number, that differentiates electrons. And I will come back to that in a minute, because it's possible for an electron to have the same first three quantum numbers, but it is not possible for two electrons to have all four of them, because those two electrons are going to be differentiated by the spin number. Now, let's take this information and apply it to writing orbital diagrams for particular atoms, and let's see the difference between an orbital diagram and electron configuration. So the easiest place to start with this is hydrogen, because it's the simplest scenario. It has a single electron because the atomic number is 1. So if I was to write the electron configuration, I would write 1s1 like that. Now, when you look at this designation, what do you see here in terms of quantum numbers? Well, you can see right away that the n number is defined. This is the n. So we know that this electron is in energy level 1. Secondly, we know that this electron is in an s orbital, so we also have defined the shape. However, we know nothing about the condition of the other two quantum numbers. So this is the importance of an orbital diagram. If we want to know the condition of the other quantum numbers, then we can write an orbital diagram for this. So this is the way we do it. The horizontal platform is a way of indicating a notation for the orientation. All right. Underneath this, I'm going to define what it is. It's a 1s orbital. So we know that this is in energy level 1. We've defined n. We know the shape is a sphere. And then we know that it has only one orientation, and that's where the singular platform comes in at. And then what we're going to do is establish the electron as an arrow. And we're either going to use a half arrow or we're going to use a whole arrow. It really doesn't matter what you do. But whatever you do, don't mix and match them. Pick one or the other to work with. And so what I'm going to do is go ahead and put the electron in here as a half arrow that's pointed up. Now, whether or not the arrow is pointed up is essentially arbitrary, because again, we don't know whether the electron is spinning to the left or to the right. And pointing the arrow up doesn't mean right or left. It's a conventional thing. Most of the time what I do in my class is write my first electron going in up. But you could just as well have done this for the same result, or used a whole arrow. And it doesn't make any difference. But what this does tell you now is that we can, by observing this notation, we know about all 4 quantum numbers of this particular electron. We know it's an energy level 1. We know its shape. We know it only has one kind of orientation. And because we're using an arrow that has a distinct directionality to it, we also know it has a defined spin. We don't know which direction it's going in, but we do know, we're acknowledging the fact that it is spinning either right or left. Right now, let's look at a more complex example in the interest of time. So here's lithium. All right, and the reason I'm picking on this is because now we're going to apply a couple different rules. The first rule we're going to apply will be the Aufbau principle. So the electron configuration for this is going to be the 1s2. So we fill the energy level 1 first, and then we move out with the last electron into energy level 2. So this is going to be 2s1. Now the orbital diagram for this is going to look like this. Let me change my color here. All right, the first 2 electrons are in energy level 1. So I write the notation this way. The platform I've drawn here tells us that there's only one kind of orientation, and then I've got 2 electrons in here, and to indicate that they have to be here with opposite spins, I'm going to write my electrons like this. So from a conventional point of view, the first arrow up, the second arrow down. So based on this notation, we know all 4 quantum numbers essentially for the 2 electrons that are in energy level 1. Now for energy level 2, I'm going to do this. So we know that this platform is energy level 2. Again, the shape is an s orbital. The platform indicates that there's only one kind of orientation. We have a single electron, so I'm going to put it in like that. And that would be the orbital diagram for lithium. All right. Now let's go ahead and move to nitrogen. All right. It has an atomic number of 7. So its electron configuration would be 1s2, 2s2, 2p3. All right. I'm going to bring back a little bit of review here. This is our valence. And there's a total of 5 electrons, which there should be because nitrogen is in group 5a. Now, let's take a look at our orbital diagram for this. And I'm going to introduce a new principle. And the new principle is what's called Hunds Rule. And what Hunds Rule says is that the lowest energy configuration for any atom is the one with the most unpaired electrons. Most unpaired electrons. All right, now, what do I mean by this? So let's look at the electron configuration for this. So first I'm going to draw the 1s, and there are 2 electrons in it, so we'll do that. The next is the 2s. The platform indicates that there's only one kind of orientation here, but now we got the 2p. And remember that in the 2p series, that there are a total of 6 possible spaces for electrons in that. There are literally 3 suborbitals for this. 3 different orientations. So I'm going to indicate that using 3 platforms, and I'm going to label this as being the 2p series like that. Each of my platforms is a specific orientation and can hold a maximum of 2 electrons. Now we have 3 electrons to go. How are we going to put them in here? So what we're going to do is follow Hunds Rule. We don't want to pair them up. So what I'm going to do is I'm going to put 1 electron in each of my orbitals. Like this. Because this maximizes the unpaired electrons. If we had chosen another way to do this, like for example, I would put I'll put an alternative down here that a novice might do, and I'll change the color of this. You know, a novice might have done this. They might have put the first two electrons paired up together in the first orbital, and then put the second one. Perhaps they would put it here or in this other orbital. And this would be incorrect. And the reason it is because notice that we've paired these two electrons up. This situation here is higher in potential energy. And I'll just abbreviate potential energy. This is higher in potential energy than the system up here. Because up here we've maintained each of these electrons, remembering that each of these has got a negative charge on it that is the same in magnitude. And so to put them together then in a suborbital together, you've got you're going to be dealing with a situation where there is net repulsion. And remember, this is offset, therefore, by the fact that the electrons have opposite spins, which creates this magnetic attraction that offsets the repulsion. But the whole point is that given the chance physically, atoms will maintain unpaired electrons until they have to be paired up. So if we look at the next example, I can illustrate what's going to happen here. So if we look at oxygen, it has 8 electrons instead of 7. Its configuration is going to be 1s2, 2s2, 2p4. All right, so 4, 5, 6, 7, 8. And again, here is your valence, just to review that. And then our orbital diagram is going to look like this. So we're going to have the 1s, and there are 2 electrons in it. Again, the 2s has only got one kind of orientation, so there's only one platform, and there are 2 electrons in it. The 2p has got 3 options, essentially. So I put 3 platforms down. Each platform can hold a maximum of 2 electrons. I put 1 electron into each platform, and I do my counting. This is 3, 4, 5, 6, 7, so we're short 1 electron. And what we're going to do is we're going to place that electron. This is conventional now. I'm going to put that electron here because we have to pair up one of these 3 platforms. And when I say conventional, I come back and I work left to right. But we could have put this electron on the middle platform or even on the end platform. It wouldn't make any difference. But the main point is we don't pair the electrons up till we have to. Now, I will give you a quick consequence of this stuff because this is real life stuff. If you look at your periodic trends, all right, any teacher worth their salt is going to teach you that ionization energy required to remove an electron as you move left to right across the periodic table, that trend will show increasing ionization energy. However, if you compare the first ionization of nitrogen, so to remove one of these unpaired electrons, and then we shift to the right and we look at the first ionization of oxygen, it turns out that the first ionization of oxygen is actually less energy than the first ionization of nitrogen. And the reason for this is because this electron is paired up. So its neighboring electron is actually repulsing it. And because of that additional repulsion, it's easier to remove the first electron from oxygen than it is from nitrogen. So nitrogen's singular electrons in the 2p shell represent a lower potential energy system than the situation is for oxygen. Right? And with that, I'm going to go ahead and close this video.